Hey, how's it going, everyone? Welcome to the third part of Networks and Graphs. So today we're going to have a look at walks, trails, paths, cycles, and circuits. So we're going to have a lot of definitions to add to your glossary of terms. In the past video, we had a look at planar graphs. So a planar graph, remember, is a graph that has no edges that cross each other. We're looking at first off is walks. So in planar graphs we can define a walk as a sequence of edges and look at various sequences or pathways through the network. So sometimes you wish to have a walk that goes through all the nodes only once. For example, a traveling salesperson who wants to visit each town once. So you've got lots of different towns and you've got a salesperson. He wants to go to every town. There might be one business in each town. So he needs to visit each town exactly once. Sometimes you may wish to use all the edges only once, such as a road repair, repairing all the roads in the Shire. So, walks. There are different ways for naming a walk. For example, consider the traveling from one node to node 3 in the figure. So we're starting off with our first. So we're starting off over here at node number 1 or vertex 1, and we want to get to vertex 3. So there's a couple of different ways we can do that. The obvious one, I can go from A, or go through walk number A, edge number B, to get to vertex 3. So I can go to A and B. I can also, specifically, I'd go from vertex 1, 2 to 3, as it's talking about there. An alternative path, I could actually go from 1 to 5, and then from 5 to 3. Or I could go from 1 to 5, 1 to 5, and then from 5 to 4, and then from 4 to 3. So there's lots of different ways I can do that. Depending on the situation I might want to go through the quickest path because I don't have enough time to go through all the towns. Another example might be a postie. So getting from one house to another, delivering all the letters to each house. So if he has specifically a important parcel that he wants to deliver as soon as he can to number 3, well, the quickest way would be from 1 to 2 to 3, etc. So that's a walk. So connected graphs is if there is a walk between all the possible vertices, then it is called a connected graph. Little example on the side over here, we've got a graph and we've got walks between 2 to 3 and all the other vertices, but at the moment I can't go from 2 to 1. So this graph is not connected. Okay, because if I start over here, I could go to 3. Oh, can't see that. If I start over here, I can go to 3, I can go to 2, but from 2 at the moment I can't get to vertex 1. So if we had a connection between 2 and 1, it would therefore be a connected. So this one over here is connected because I can start from any vertex and get to any other vertex. Over here, I can't get to 1 or 4 if I start over here. Euler trails. So a trail is a walk in which no edges are repeated. An Euler trail is one which uses every edge exactly once. So I might have this network here, and I might start at this vertex over here. So a trail, I can just simply go from 1 to 2, from 2 to 3, and then 3 to 4, and that's all good. So that would be a trail. It's not an Euler trail because I haven't used these two paths over here. Now, I don't think this situation will work for a Euler trail. Let's just have a look. So if I started over here, right, I can go from there to there. I can go from that one to that one. I could go back along that path. There we go. So I can do that one. So that is an Euler trail because I can use every edge exactly once. Doesn't matter that I've got repeated vertices. I haven't repeated edges. So for an Euler trail to exist, all the vertices must be of an even degree, or there must be exactly two vertices of odd degree. So if we go back over here, I've got vertex 1 and vertex 3. This is number 3 over here. So we've got two. Oh, hang on, no, 3 is not a vertex 4. So the degree is 1. The degree over here was 3. So there's my two odd degrees. At vertex 3, I had the degree is 4, and over here at vertex 2, the degree was 2. So I've got two odd degree vertices, and I've got two even degrees. So it did work in the end, because for this Euler trail to exist, all vertices must be even degree, or exactly two vertices of odd degree. The second option is if the degrees of all the vertices are even numbers, we can start at any vertex, and in this case the starting vertex and ending vertex are the same. The third option is, actually I'll have a look at number 2. So just as an example, alright, so I've got 3 vertices, and I'm going to make every vertex with even degree. So it's saying that this is actually an Euler path, and I can actually start at any vertex and I'll be able to go through every edge exactly once. So here's one option. Alright, and I ended up at the same position. So there we go, just as a quick little example. The third option, if there is two vertices whose degree is an odd number, we have to start at one of those points. So as I did before, I started at vertex 1, which had odd degree. No, sorry, I started over here at 4, had degree 1, ended up at the other odd degree. Okay, so definition for Euler trails to exist would be worth writing in your glossary of terms. Work example 10. Let's have a look. So, using the following figure, identify an Euler trail. First thing to look for is, have we got all even degrees? So degree 2, 2, that one's a 3, a 2 and a 3. So no, they're not all degree 2, but I do have only 2 vertices with degree which is odd. So if we have a look at our definition, number 3 said if there's two vertices whose degree is an odd number, we have to use either one of those as our starting point. So I'm going to pick degree number, vertex number 3. So I'm going to start at 3, and hopefully I end up at 5, because that's my other odd degree. So it shouldn't really matter which way I go. So I'm going to start at 3. I'm going to go to 2, from 2 to 1, from 1 to 5. From here, it would be worth going up to 3 again, going down to 4, and then back to 5. So there's an Euler trail. There's different ways you can do it. That's my example that I've done. And if I was to write it out, I started with B, I went through A next, and then I went to C, and then F, and then D, and then E. Okay. Euler circuits, so we've got 2 more definitions, add to your terms. So a circuit is a trail beginning and ending at the same vertex. An Euler circuit is an Euler trail where the starting and ending vertices are the same. So technically, slightly different. So a circuit means that I start at one point and I get to another. So I start at this point here. So a circuit means that I can start there, go to that one, go through that one, I can go through that one, and then go through that one. So I start and end at the same spot, but I haven't used all the edges. I haven't used that one and that one, and that's okay because it's just a circuit. Whereas an Euler circuit is going to be the same thing, except I have to also have the Euler trail, meaning I have to go through every other edge as well. So same situation. So I probably want to start over here, and I'm going to go along that edge, along that edge, along that edge, along that one, and end up over there. Unfortunately, this one is not a Euler circuit. Even though I've used all the edges, I haven't started and ended at the same vertex. So it is important to note that an Euler circuit cannot exist for planar graphs that have any vertices whose degree is odd. So over here, if you have a look, this one was a degree 3, this one was degree 3 as well, which means it's not a Euler circuit because I've got a degree of 3. Now, just going to adjust that so that they are even degrees. So now I'm going to start at the same spot. I'm going to go through that one, go through that one, go through that one, go through that one. Then I can go through there, 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 and there. So there we go. End up at the same spot because all of the vertices are even degree. Worked example 11. So find an Euler circuit for the planar graph shown. Just check all the degree. So 2, 2, 2, 2, and 2. So that's good. They're all even degrees, which means from my definition, an Euler circuit should exist. So if I start at 2, I'll go to 3, go to 4, go to 5, go to 1, and back to 2. So there's an Euler circuit. Pretty simple for that example. For some networks, it's not always easy to figure out the Euler circuit, and sometimes can be quite difficult. Uh, Fortunately, we have a algorithm that can help us determine where the Euler circuit exists. So consider a network where all the vertices are even degree. As I said before, for an Euler circuit to exist, all the vertices need to be even. So we've got V equals 1, 2, 3, etc. Be the list of the vertices. Step 1, choose a starting vertex from the list and call this vertex A. Step 2, from vertex A, find the smallest possible path which returns to vertex A. This is a sub-circuit of the original network. Let S be the list of vertices in the sub-network. So from over here, alright, I started at this spot here and I went around all the quickest, shortest path back to that original spot. So that was essentially what I was doing for step 2. Step 3, for each vertex in S, which is the sub-circuit, choose a single vertex in turn as the starting vertex of a different sub-circuit. It should be also as small as possible and not use any previously used edge. So from my example before, right, my first sub-circuit, right, used all the outside edges, and then my second subset used all the inside edges. Step 4, for each of these new subcircuits, add any new vertices to the list. Repeat steps 3 and 4 until there are no vertices and join the subcircuits in their intersection points. So in your books it would be worth writing out these steps. Looks complicated, but we'll go through an example in a moment. So I've got worked example 12. Find one possible Euler circuit for the network shown using the Euler circuit algorithm. So I'll just redraw this out. Alright, so it's not as straightforward to determine where that Euler circuit exists. So using the algorithm, we look at step 1, choose a starting vertex from the list V and call this vertex A. So, well, actually, the step before that, got to check that they're all even vertices, in which case it is. So we've got 2, 4, 2, 2, 4, 2, 2, 2, 4, 2, and 2. So they're all even, which is good. So I'm going to start over here at A. And step 2 says from A, find the smallest possible path which returns to vertex A. So the smallest possible path that returns to vertex A. In this case, it's this one here. So that's the shortest possible path. So on the side, I'm going to say our subset S is, so we've got 1, 2, 3. So 1, 2, and 3. That's my path. From vertex 2, so step 3, for each vertex in S, choose a single vertex in turn as the starting vertex of the different subset. Okay, so we've already used 1, so moving on to 2. So we're starting at 2 and now do the same thing. So the shortest possible path for vertex 2. So from 2 I can go up, 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 and over there. So my second subset S is going to be from 2 to 4, and then 4 to 5, and then from 5 to 6, then from 6 back to 2. So, because I've got new vertices not contained in that one, I now add them together. So my sub new S is going to be from 1 to 2 to 3, and then from 3 to 4 to 5 and 6. Now, going back to this one over here, from 3, there's also another sub-circuit. So from 3, I can go down to 9 and 8 to 7 to 6 to 10 and then back to 3. So I went from 3 to 9 to 8, 7, 6, 10 and back to 3. So now I add that to that S. So S is now going to be from 1 to 2 to 3 to 4 to 5 to 6, from 7, 8, 9 and 10. And that's equal to the number of vertices. So we stop. So my Euler circuit is applying step 6. So join the sub-circuits at their intersection points. So I started at 1 and I went to 2. From 2, I have the subset starting for the next one. So I actually need to go to 4 to 5 to 6 and then I go back to 2. From 2, so I started at 1, went to 2. Now 2 is connected to that one. I went through all those and then I went back to 6. And from 6 to 2. Now I finish off this first sub-circuit, which was 3. Goes to 3. However, from 3, that starts my new sub-circuit. So from 3, I actually should go to 9, which is down, then 8, 7, 6, 10, and then back to 3, and then finishing off, I go back to 1. So there is my Euler circuit. So a little bit complicated to start with. So it's about creating these subsets, and then final thing is connecting them all together. Bit of practice and it'll make a bit more sense. Got a couple more definitions. So we've got paths and cycles. So a path is a walk in which no vertices are repeated, except for the possibility of starting and finishing. A cycle is a path beginning and ending at the same vertex. So in Euler trails and circuits, each edge was used exactly once, whereas we can use vertices as many times as we want. Now we're looking at the situation where we want to visit every vertex exactly once. So it doesn't matter how many times we use each edge. A Hamilton path, however, uses every vertex exactly once. So it is important to note that not all edges need to be used. So we've got path, cycle, and then Hamiltonian path. So example 13, determine the Hamiltonian path in the planar graph below. So just going back, a Hamiltonian path uses every vertex exactly once. So I've got 2, 3, 4, 1, and 5. So every vertex exactly once. Well, I can draw starting at 1. Since there are no vertices with degree 1, I can start any spot I want. If I had another thing over here, vertex over here, with no other connection other than that one, I'd have to start over here. But I don't, so it's okay. So I'm going to start over at this one down here, and I might choose to go up, across, down, and across. So there's a Hamiltonian path, because I'm using every vertex exactly once. Now, a Hamiltonian cycle is a Hamiltonian path which starts and finishes at the same vertex. So another definition. So the last example is basically the same situation, but I want to determine the Hamiltonian path, the Hamiltonian cycle in the planar graph. So again, I'm going to start at vertex 1. And I want to end up at vertex 1. So starting from here, I want to visit every vertex exactly once, but I want to end up back at 1. So if I go through that pathway there, I'll start and end at the same spot there. So I just haven't used that one, which is okay. So that's chapter 9.4. Have a go at the questions and stay tuned for the next video. Thanks for watching.